All right, welcome back to our deep dive into dynamic topology. So last time, we got our heads around the idea of locally connected sets, right? The basic idea was that for any point in our set, we can always find a small, connected neighborhood around it. It kind of gives us this feeling that a space is, nicely put together on a micro level, point by point.
But that raises a really interesting question. How consistent is that property across the entire space? Today, we're going to crank things up a notch. We're building on that foundation to explore two stronger, much more precise types of connectedness. These don't just work point by point. They lay down the law for the whole set at once. So let's get into it.
Okay, just a super quick refresher on what we covered last time. This is that formal definition. It basically guarantees that no matter how much you zoom in on a point, you can always find a tiny connected chunk of the set right there. But here's the crucial part to remember. The smallness you need, that little open set VP, could be totally different for every single point. What works for one spot might not work for another one right next to it. So let's introduce our first new idea, property S. This adds a really important new rule to the game. It says that for any small size you can possibly imagine, let's call that size epsilon, you can always cover the entire set with a finite number of connected pieces. And each one of those pieces has to be smaller than the epsilon you picked. The magic word here, the one to really focus on, is finite. The best way to think about this is like you're tiling a floor with a mosaic. You can tell the tile maker, hey, I want all my tiles to be smaller than 1 centimeter, and they can do it. Okay, smaller than 1 millimeter, they can do that too. No matter how small you demand the tiles to be, you'll only ever need a finite number of them to cover the whole floor. A space with property S is just like that. It's always made of a finite number of tiny connected bits. Now for our second concept, uniformly locally connected. This one makes the rules even stricter. It says, for any target size epsilon you want your final connected piece to be, you can find one single distance, let's call it delta, that works for the entire set. This is huge. It means if you pick any 2 points anywhere in the set and they're closer than that universal delta, you are absolutely guaranteed that they both exist inside a single connected piece that's smaller than your target epsilon. That one delta is like a master key for the entire space.
So let's just put these side by side because this is the whole ballgame right here. The differences between a local rule and a global one. With standard local connectedness, that connectedness rule can change all over the place. But with uniform local connectedness, we have one rule, one delta, that applies everywhere, consistently across the whole space. You can see why this is a much, much stronger and more restrictive property. And what's really cool is how these three ideas fit together. There's a clear hierarchy, a pecking order. At the very top, the strongest condition is uniformly locally connected. If a space has that, it automatically has property S. And if it has property S, well, then it's for sure locally connected. But, and this is super important, it doesn't work the other way around. A space can be locally connected without having the much stricter property S.
So you might be thinking, okay, this is getting pretty abstract. Why do we need all this precision? And that is a totally fair question. The answer is that these properties become incredibly powerful tools when we want to figure out what happens when we start transforming spaces with functions. Let me show you what I mean. Here's a key theorem, straight from Wyburn's text. It says property S is invariant under uniformly continuous mappings. Now, invariant is just a fancy way of saying the property is preserved. So if you take a space that you know has property S and you apply a nice, well-behaved function to it, a uniformly continuous one, the new space you get out on the other side is absolutely guaranteed to also have property S. The property survives the transformation. And here's the beautiful logic behind it. You start with your space X, which we know is like a finite mosaic of small connected pieces. Now, a uniformly continuous function is well-behaved. It promises not to stretch things out uncontrollably. So when you use that function to map those pieces over to your new space, Y, they stay connected, they stay small, and crucially, you still have a finite number of them. So there you have it. The new space Y is also a finite mosaic of small connected pieces. Property S survived the journey. So we've basically just built a really precise language for talking about the different levels of connectedness, from a simple local property to a really strong uniform one. And we've seen that these aren't just abstract definitions. They describe the fundamental texture of a space, a texture that can actually be preserved under certain transformations. Next time, we're going to see how these powerful tools unlock even deeper insights into the fascinating world of dynamic topology.